Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today we're continuing with our look at the reciprocal system Macrocosmos database. Remember, there are two modules to the reciprocal system database, the Macrocosmos database and the Microcosmos database. You can see the menus of these two modules here. This is, on the left side is the Macrocosmos database, and on the right side is the Microcosmos database. We've already covered the universe as a whole, galaxy clusters and groups, galaxies and star clusters. So now we're going to cover stars. So we'll go here, and we'll go through each of the fields in turn. So we're going to look at the record for the sun. So the star name is here, obviously. Any alternate names for the star would be in this field. In this case, it's Sol. The form number is 1. If you wanted to have multiple records for a single object, you could duplicate the record by pressing Control-D and then incrementing the form so you know that it's not a duplicate record per se, but you just want to put in other data. The main fission element here is lutetium. Now, for other stars other than the sun, there would be a location year, like 2000.0. The right ascension in hours, minutes, and seconds. The declination, degrees, minutes, and seconds. Just to show you what that looks like, we'll just click here at the bottom and go to the next star. This is Proxima Centauri, and there you can see these are filled out for Proxima Centauri. But let's go back to the sun. In these fields, you can put in whatever photos or videos you have. If you're an amateur astronomer or professional astronomer, you can put your videos or fields here. Just scroll down. You can see how many different records I have here, or I should say videos or pictures, and you can enter in a new one here. Now down here we have events. So these are specific events rather than general pictures or videos. These are specific events or happenings. And you can just look at these. I mean, look at all. A lot of these come from NASA, of course. These are public domain pictures. I'm not going to scroll through the whole thing, but you can see there are a lot included in the database. Well, there wouldn't be any galactic coordinates here, but there might be for another star. I don't think. Let me just look at Proxima Centauri. No, I don't have it for that. But if that's the coordinates you prefer, you can use that. And then over here you have the planets, like Earth and Jupiter. So, for example, let's say I click here in Jupiter. I can click this button here, and it'll take me right to Jupiter. And then I can come back here to the parent object, which is the sun. I can click that, and I'm back to the sun. Okay? So that's what a relational database does. The distance in astronomical units, this is a formula for computing the spacing of the planets. So that's A0 and that's K. That's in astronomical units. So I'm not going to go into that today, but that's kind of interesting. We have a formula in the reciprocal system similar to the Bode equation, if you're familiar with that. Now, the class of the star is yellow dwarf, and here are all the different possibilities. Look at all these. And you can even, if I've missed one, you can edit this list and you can add your own classification if you like. I'm just going to leave this alone. Let's see, it's yellow dwarf. The star emittance in ergs per second per centimeter squared is 6.319 times 10 to the 10th. Minor bodies are listed here. So look at all these. These are asteroids and comets. So you can add them in. And again, it's relational. So let's see. Let's pick one just to jump to, I don't know, the C. This one is interesting. This one. Click there. Click minor bodies, the tab, and there it is. Oh, well, it goes to the Earth, but that's all right. let's go back. Click on stars. Now the spectral type is G2V. Put that in. The effective temperature is 5771.8 degrees Kelvin. That's the central, the central temperature. I'm not going to do that here. And that's determined by the star spectral type. You're going to have to see existence, interactions, and computational treaties in the reciprocal system to get that. And the reciprocal system star class is 2B. So that means second generation, that's what the 2 is, and B means main sequence. So here are the possible types of star classes in the reciprocal system. 1A, which is a red giant first cycle. 1B, main sequence first cycle. 2C, red giant second cycle. 2D, white dwarf second cycle. 2B, which is main sequence second cycle, that's the sun. 3C is red giant third cycle. 3D is white dwarf third cycle. 3B is main sequence third cycle. 4C is red giant fourth cycle. 4D is white dwarf fourth cycle. 4B is main sequence fourth cycle. And then we have pulsar end stage as well. So that's that. Now we come over here. This would be for other stars, the radial velocity. Let's see, this is the proper motion transverse RA. Let me see if I have that for, yeah, I do have that for Proxima Centauri. Minus 3775.7. That's milliarc seconds per year. See, it's very nice when you move the mouse over a field. If it's not clear, it'll explain it for you. It's a very nice feature. I'll just come back to the sun, and we have angular momentum, grams centimeter squared per second. We have the revolution velocity 220.0. Sidereal and synodic periods, that's for the rotation, 24.47, 27.28. Speed relative to the CMBR is 370 kilometers per second. Distance, parseconds, of course there's no distance really in terms of parseconds and light years. It's way less than light, way less than a parsec. From the center of the galaxy, we're at 8.5 parsecs away, or 27.7 light years. These are the magnetic fields in Gauss. To convert to Tesla, multiply the values by 10 to the minus fourth, of course. So we have star spots. Let's see, what is this polar? Alright. Over chromospheric network, phages, and prominences. These are magnetic fields. You can see kind of interesting what the magnetic fields are for the different aspects of the sun. Now these are the luminosities, the total bolometric. In terms of the sun, these are all going to be 1, of course. And ergs per second, total bolometric is 0.827 times 10 to the 33rd ergs per second. Let's see all these other ones here now. In a lot of cases, like Proxima Centauri, we know what the optical is. That's in here. It's kind of weak compared to the sun. But it's kind of difficult getting this data, but it's here just in case you have the data. The mass is going to be 1 solar mass unit, of course, which comes out to 1.98 times 10 to the 33rd grams. And then we have the gravitational limits. The first gravitational limit is 1.11 parsecs, and the second is 4.102.34 parsecs. Total mass to luminosity ratio is, of course, 1, because that's how it's defined for the sun. And the mass luminosity ratio for Proxima Centauri is 72.35 to 94 there. Okay, so let's go back to the sun, our favorite star. Let's see, the main density 1.411 grams per centimeter cubed. A little bit denser than water, which is kind of interesting. Let's see, what is this one? 0.951 times 10 to the minus 1. rho sub s, moment of inertia, and here's the equation. There's an equation given there. I'm not going to read it. Grams centimeter squared. That just basically means 1. You know, if I go, here, let's get approximately right. So that's like 4.36 times the density of the sun. That's what that is. This could be rounded up to 1, I suppose. Surface gravity, 27.412 centimeters per second squared. Escape velocity, 17.58 kilometers per second. I don't have anything for sound and gas dust mass, but there has to be an inflow of cold dust and gas moving into the sun because it's accreting everything within its gravitational limit. So most astronomers focus on the solar wind, but they don't consider that the sun is sucking in all kinds of dust and gas within its first gravitational limit. Photospheric abundance, this is in terms of, let's see, in fractions, right? So 0.734 rather for hydrogen, 0.246 for helium, and the rest for higher elements. Overall metallicity, it's about 0 here. Percent is 100, of course. That's just by definition relative to the sun. Age in years, 4.6 billion years, and that just about does it. On the notes field, you can put whatever you want. By the way, if this were a binary star, you would have associated stars listed here. I want to take a look at them. Let me just read the first. Some astronomers believe that the sun's distance from the center of the galaxy is 8 kiloparsecs. Current data for the sun is given at https://google.com site, so on and so forth. I'm not going to read the whole thing. That reference also says that the mass is slightly lower than 2 e times 10 to the 33 grams. So, and then I have a lengthy quote from page 62 of Larson's Universe of Motion. I'll just read the first couple sentences. The observed fluctuations in sunspot activity are particularly noticeable. The origin of these spots is unknown, but no doubt they are initiated in some manner by the energy production process. Hence, they may be giving us an indication of the variations in the output of that process that would be expected from the periodic changes. And you can read the rest of it. Alright, so that pretty much covers what we have for stars. But let me just see if I can find a binary star here. Yeah, here's one. Antares A. There's Antares B. So this is definitely a binary. This one is a red giant. And this one, let's see if this works. I go here. And there's Antares B. I don't have much information on this one, but the special type is B2. Now, again, there's a lot of data for spectral type. Alright, well anyway, so that's where you put the associated stars anyway. I can click this to go back to the first record. Now I gotta show all. And then I gotta go. There, now we get to the sun. Okay. Alright, that wraps it up for today. That covers the layout for stars in the Reciprocal System Macrocosmos database. For the simplest possible explanation of the reciprocal system of theory, please obtain my work, The Unmysterious Universe. It has all the concepts, many diagrams, very easy to read. Now, if you do want all the mathematics, however, please obtain my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. It has thousands of equations. It's 111 pages in the PDF file, it's 111 slides in the PowerPoint file. As I said, thousands of equations, diagrams, figures, drawings, you name it, it's all in there. It'll take you months to get through it. Then, after you get through that, then you consider getting the 2 database modules. Now, if I close out this layout here for stars, we'll get back to the main menu. And you can see that I cover the universe as a whole, Galaxy clusters and groups. Galaxy star cluster stars, planets, moons, minor bodies like asteroids and comets, nebulae, gas and dust, and voids. This is a typical void, incidentally, if you haven't heard of such a thing. And there's an events tab if you just want to look at videos or photos in the system. There's also a great graphing package. Now, the Reciprocal System Macrocosmos database has all the properties for matter, and including solid matter properties and atomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and spectra. Also has all the properties for liquid, vapor, and gas matter properties, volume and density, specific heat, energy and entropy, viscosity and surface temperature, and electrical and thermal conductivity. And of course, this module also contains properties for photons and for cosmic elements and subatomic particles. Cosmic elements appear to us as what we call mesons because they have a mass in between that of a charged electron and a proton in general, usually. It could be as high as deuterium, cosmic deuterium, for example. But most of them, the mesons, are less mass than a proton. And this also has a nice graphing package as well. Now, my theoretical physics mentor, Julie B. Larson, was not only a great theoretical physicist, but he was also a great theoretical economist. And I've made his work in economics also completely computational. Optimal economist, an implementation of Larsonian econophysics includes both the microeconomics and macroeconomics. The microeconomics of individuals, businesses, and business sectors, and the macroeconomic calculations for whole countries or regions. Very complete, totally supersedes Keynesian economics, just as the reciprocal system totally supersedes so-called modern physics. All right, so please study the reciprocal system and prove it for yourself. Thanks for your attention.